You're asking about the different series, the Lyman, Paschen, and all that stuff. Okay, Lyman. Then there's the Balmer, goes in between, actually, to be complete. And then we have the Paschen. Okay, and wherefore and why for. Okay, that's good. Yes?
I was wondering if you could go over what's important about pulses and
Pulses, yes. That's a very good subject. Pulses. Okay, yes, thank you. That's a good one. Okay. You know, for those of you who were here the last time, let me add something else. One of the students brought up, perhaps it was you no, it was somebody else that brought up the idea that there were these energy levels, and then there's KT, and there's HF, H times the frequency, and then there's electron collisions. How does it all hang together? And I started to use an analogy of putting shelves in a closet. And on the way home, I thought that's actually a very good analogy, but I didn't carry it far enough. I hadn't really thought it through before. That's what's wonderful about being a teacher. I get these great questions, and then I start thinking about things, and it illuminates the thing. So let me, as an introduction to some of these ideas, go over that analogy again. Namely, we have these so-called quantum levels. Okay, so is there some other way of thinking about it? So I started to talk about, suppose I have a closet of a certain shape. And I can have them of odd shapes. I could even, that's stretching the analogy a little bit. And then I'm trying to put shelves in this closet. Now, the point is that what's unusual about quantum theory is that there are certain quantum rules that apply. Some quantization is forced on us. Now, for example, in this analogy, it might be that you go to a hardware store and they only have boards of quantized lengths. Let's say 3 feet, 4 feet, 5 feet, so on. They're quantized. So they're forcing a quantized level. Now that is not exactly how you would do carpentry. You would cut it to shape. Classically, you could cut the thing to any shape you wanted. In other words, if you wanted a shelf here, you would just cut it to that length and be done with it, right? That's classical. It can have any energy, it can have any shape. So that's the classical thing. But quantum says, no, you can't cut it to any length you want. You have to take what I have. And you have to buy it. So what that does, it forces levels so that you can put in a shelf at 3 feet separation, or you can put in a shelf at 4 feet, or you can put in a shelf at 5 feet, because you've been forced to quantize things. So that's what quantum theory does. It's in a certain sense, artificially forcing you to do that. And the reason behind it is that there are standing waves, and the standing waves take a certain length in here, and they want to be like, for example, Bohr said, the angular momentum has to be some, again, my ends, bad ends, h bar. So he's saying the quantity of angular momentum in the case of a circular orbit, I'm saying you can't cut your Planck to any orbit you want. You must have the orbit n times, have an angular momentum n times this number, and that'll give you the right answer. That's what he's saying. It's a peculiar thing. But he's just saying, I'm forcing you to say, I can have one h bar, namely I can have a 1 foot Planck, I can have a 2 foot Planck, a 3 foot. Oh, that's funny, a Planck's 1 foot Planck. Oh my God, that's even a better analogy. I hadn't thought of that too. That's very good. So these are different Plancks. Okay. All right. Yeah. So you can have 1 Planck or 2. Oh, that's really good. I should post that. So I'll use that next time. Yeah. the other joke that I have about that is that after this, we're going to go to the H bar and have an Einstein of beer. No. We don't want to push that too far. So that's the trick. That's the trick of quantization. For some reason, Bohr didn't really know the reason, but he just said, if you do that, you get the right answer. Later on, Schrödinger, here's a lady that asked about this structure. Later on, Schrödinger and de Broglie explained that you want to have a wave that just fits in here, so that one way of looking at it, if the wave means something, then it should have one value at every place. If the wave has more than one value at the same place, it can't have much physical meaning. So, for example, if this wave didn't come back on itself, it would have two values at this point. It would have had this value and that value. So one way of saying it is that the wave must fit into the shape and have one particular amplitude at that place. Why that is again mysterious, but the good thing about it is that it works. So if you want to think about quantum theory, what it's telling you is that in any given situation, if there's a cyclic motion, if the thing is bouncing back and forth, or if it's riding, see again, suppose you had a potential like this, and you're only allowed certain, let's say your closet was shaped like this, and you're only allowed certain planks. Well, you can put in one or two, let's see, about up here maybe, and then maybe a 3-foot board up here, and you'll notice that the energy levels on those shelves will be some peculiar number. The gravitational potential, if I put a shelf here that's 1 foot long, and I put a 2-foot shelf here and a 3-foot shelf here, the spacings will be peculiar. And those will be the energy differences, the gravitational energy differences. So the structure, you have the shape of the potential, and you're just trying to put levels in here under some quantum conditions. Here we quantize the length of the boards. No. I would keep the formulas nearby. I would know the simplest cases. We've worked on the infinite square well. You want to know the energies there. Just write that formula down. But it's very easy to derive, because in this case, you use your simple rules about wave functions, that you have 1 half wavelength, 2 half wavelengths, 3, and so on. And the wavelength by de Broglie is h over the momentum. And the energy of such a thing, we're taking here the potential energy is 0 at the bottom of the box, so we're taking that as our reference. So that the energy is purely kinetic in this case, square well potential. And so the energy is all kinetic, and that's half mv squared, right? But if you are clever, you multiply top and bottom by m, you get m squared on top, and you divide by m on the bottom. I don't know how many loops to put in my m's. Keep putting in loops till it looks like an m. And so, and this mv is momentum, right? So, mv. So another formula for that is p squared over 2m. And p is equal to h over lambda. So p h over lambda squared over 2m. H squared over lambda squared. So the point is that the energies are just proportional to lambda squared. So in the level 1, you have lambda over 2, actually, is equal to the length. And lambda, that's for the ground level, level 1, say, 1/2 wavelength. Then you have 2/2 wavelengths. So the wavelength is equal to L. So you can just put in those lambdas in here. So it's sort of 1/2m h squared. And lambda is given in terms of, so n lambda over 2 is equal to the length. So you can substitute. Is this anything new? Am I wasting my time? Is this very familiar to you? Was it worth doing again? So the idea is then that, okay, let's make sure we have that. You have the kinetic energy is equal to h squared over 2m lambda. But lambda is equal to, or n lambdas over 2 are equal to L. And these are the different n levels. 1/2 wavelength, 2, 3, 4. So you can get that lambda is equal to 2L over n. And if we plug that in here, 2L over n squared, you get the energy levels are h squared over 2, well, the 2 squared, that makes a 4 times 2 makes 8 out in front, m, L squared on the bottom, and the n squared comes up on top. So that's the formula, very simply derived for the energy levels in a box, which, as I pointed out last time, they increase, those kinds of, in a box, the quantum condition, namely, this is your quantum condition in this case, that, and this is the quantum condition too, that the wavelengths have to fit into the box. The energy levels increase as the square. So if you have one here, this one is 4 times higher. The next one is 9 times higher, if that's E0. The next one is at 4 E0. The next one is at 9 E0, and so on, because of this n squared thing. You're familiar with that? So in this particular geometry, the quantum condition forces these shelves to have a certain spacing. And in the case of a square box, the spacing increases as you go up, goes up as the square. In the case of a harmonic oscillator, it turns out that the quantum condition forces the spacings to be equally spaced. So between each of these, you're going to get 1h times the frequency of the lowest state. So the first state has an energy, actually a half HF. The next one is 1.5, 2.5, so on. So the spacing is equally spaced in this case. And the third case that we know about is the hydrogen atom, where the potential is the shape of the closet, as it were, that we're putting levels into, is such that the energy levels start out with a big jump, and they get smaller and smaller. It goes as 1 over n squared. So I guess the energy of the harmonic oscillator, the nth state, is sort of n, well, it's actually n, I keep doing that, n plus a half h times f, 0, of the ground state. In other words, the levels are in integral multiples of the ground state. In the case of the box, it goes as n squared of the ground state. In the case of the hydrogen atom, it goes as 1 over n squared. So you want to know those basic differences. And it's just due to the different shapes of the potential that it's trying to fit. What?
Does this only work for hydrogen atoms?
Hydrogen atoms?
I mean, sorry, the Bohr model, not the Bohr model.
The Bohr model, it's very hard to extend beyond the hydrogen atom. It works very well for 1 electron atoms. If you can somehow get down to one electron, it works very well. So in fact, it works in a number of nice cases. Well, of course, hydrogen itself is very nice, one electron. Or you could do helium, which you have two plus charges and two neutrons. But if you ionize, and supposedly it has two electrons, but if you can ionize off one of the electrons, then you'll just have one electron going around. It'll work perfectly well for ionized helium. It works pretty well for alkali metals, where you have an inner core of charges, and you have one extra electron outside. You've asked a good question, actually, there. And if you have one electron outside, it works pretty well for that, too, because these let's say you have something, could have as many as, let's say lithium. You have 3 plus charges inside. But if 2 of the electrons, say the 2 1s electrons, which we usually write 1s squared, are inside here, they screen out this one because they stand between this outer electron and this. And so you remember from way in the beginning called Gauss's law? Good thing to remember here. That is that the field, if you draw a Gaussian surface around here, and you ask, what is the electric field at that point? In other words, what is the electric field that that third electron sees? You can do a Gaussian thing and say, well, I have 2 electrons inside, and a third 3 plus charges inside. So if I draw that surface around, Gauss's law would say that the integral of E over that surface, electric field over that surface, is the charge enclosed over epsilon naught. This is the famous Gauss law, one of Maxwell's laws. And so, since the charge enclosed is only plus 1 charge, the electric field is that of 1 charge. So this lithium atom looks, a Bohr's theory would work pretty well for this one. As long as he doesn't get inside. Once he gets inside, those 2 charges there don't shield him too well. But when he's out, so it's not too bad an approximation. And the other place where it works nicely, so this would be for alkalis. The other place where it works is the case I gave you of a donor atom in a semiconductor. There it works because the donor, let's say phosphorus in silicon, it uses 4 of its 5 outer electrons to make bonds, and it has 1 extra electron. And that 1 extra electron circles around in a Bohr-like orbit about that remaining single charge. So this acts as like a hydrogen. So in fact, the model works very nicely. Bohr's model, because what you got, again, is 1 electron circling around a net charge. And so that's a place where Bohr atoms work. But if you get more complicated, like putting 2 electrons, then you got a problem, because one of the electrons is seeing the other, and it's seeing the nucleus, and it's complicated, and then you have to go up a level to Schrodinger. Okay, I hope that review. So, going back to, I'm still answering the question you asked last time. Namely, I was using the analogy of shells, trying to fit quantized shells into funny shapes. And it ends up that if you're forced by quantization to have some condition on the shells, then they're going to force you into having funny spacings between the energy levels, depending on the shape of the shell, of the closet you try and put them in. If they say, I can only use shells quantized in 1, 2, 3 feet, or 1 foot and twice that foot, or thrice that foot, that length, then you're forced into having peculiar spacings. Then the question is, how do I go from one space to another? And basically the other part of your question was, how does KT get into it? How does HF get into it? And those are the energies you're trying to use to go from one level to the other. Let's say you want to move something from this shelf to that shelf. Or what shelf is most likely to be occupied if the parcels have their choice of where to go. They want to go to the lowest state. So all those things that you mentioned, KT is thermal energy. In other words, heat. You know that heat does things. Heat can boil water. Heat can cook eggs. Heat can do things. And the measure of how much energy it has is its temperature. So all you're saying is that we're trying to give some measure of how much energy is in the heat. And the measure of that is just proportional to the temperature. And it happens that per atom or per molecule, the proportionality constant is the Boltzmann constant. Or in the case of a large amount of stuff, it's the gas constant of PV-RT. R per mole is the energy content of a mole of gas. Per molecule, another divide by Avogadro number, you get this. So that's a measure of the energy which is available in heat. Then, so that energy is going to perhaps, if you have KT, KT is sort of like saying how tall are people, as compared to say how big are dogs. You can, if you say the people are sort of like 5.5 feet. So you haven't characterized everybody. Not everybody's 5.5 feet, but roughly speaking. And if you say a dog is maybe 1 foot, or well, it's a big dog, it might be 2 feet. But there is a sort of distinct difference. If you're talking about the length of dogs, you would say 2 feet. If you're talking about the length of people, you'd say maybe 5.5 feet. So the KT is that kind of an estimate. It's a ballpark estimate because there are variations. Even within a given temperature, some particles are moving faster than others. Just like among people, there are 6-foot people and there are 5'3" people. But 5 feet is a rough estimate. So KT is this sort of statistical ballpark estimate of the energy in heat. So that's why we get kind of statistical factors when we talk about heat. This thing here, this energy over KT, that's kind of telling you some statistics, a probability of a particular energy. It varies, you see. On the other hand, so that's one sort of energy which can raise things up, and with a certain chance that there'll be if the energy is big enough, it might be able, like if there was an earthquake, you might shake things off this shelf onto this shelf if you have a big enough vibration. On the other hand, HF is a particular energy, and it's very specific. There's nothing fuzzy about that. Well, a little bit fuzzy, actually, but not very. It actually goes back, the fuzziness comes back to your question about pulses. If the pulse has a certain length, you can't really specify F precisely, because it takes a lot of Fs to make a pulse. So your point is right. So you're going to have F with a little bit of fuzz, something like that. A little fuzziness about what you mean by F, the frequency. But it's sharper. It can be sharp. In fact, with a laser, you can make it very sharp. Just what you mean by F. In that case, you know very well what you mean by the energy, HF being the energy. And then if that's a very nice way of getting things from one shelf to another. You hit it with exactly the right amount of energy, very precisely. And the other one that we have is the electrons moving. You can just sort of have moving particles. And it turns out that you can bounce electrons or throw a stone at it or something and knock it so hard that you will knock something from one shelf to another. So the energy levels are determined by the potential and some quantum conditions. And then the question is the occupancy of those levels. Things want to go into the lowest levels with the Pauli principle working, that you're only allowed 2 in each quantum state. 1 in each quantum state, 1 or 2 if you don't count spin. 1 in every quantum state is the best way to look at it. And then you have these various energies capable of moving them from in and out of those states. Or the energy being released when they jump from that up high state to the low. Yes, did you want?
I was just going to ask about that.
That's right. That's right. They
Is there what is something that would make it do that?
fall down.
Yeah.
Well, we speak of two processes. We speak of the spontaneous and the stimulated. Spontaneous means if a thing is in a higher state, it spontaneously will go down just because things tend to go to the lower level. It's not, truly it isn't quite spontaneous because there always is in space a little bit of electromagnetic energy of all kinds of wavelengths. So in a way, the world itself, if you have a hydrogen atom, if the world itself contains these electromagnetic radiations, one of them is possibly going to jiggle the thing that's in the higher state and say, okay, let's go down to the lower state. So in a certain sense, it's spontaneous, it's stimulated. The other way is that you actually put in from the outside, or that's what happens in a laser, any wave that's sort of the first one that spontaneously drops, you try to catch it, and you send it back so that it can stimulate the others of its type to go down too. So then you have the possibility of making a large number of them. So you have both spontaneous, which is not truly spontaneous because of the vibrations, natural vibrations, due to the fact that we're warm. You see, the world is warm, and we're all emitting electromagnetic radiation. So you could, well, it gets into quite an interesting story. Suppose, for example, an atom wants to decay, but you put it in a space where you exclude those waves that might stimulate it to go down. By, say, putting it in between plates where the waves that you might stimulate it can't fit in there. They're too long. And you can do that. You can slow down the spontaneous rate by putting it in a certain environment where those waves don't exist. Or you might cool the thing so cold that the world around it does not generate these stimulating waves. And those kind of tricks are what a lot of atomic physicists play with. They want to play with even the spontaneous thing that you would think nature is providing. They can interfere with that. So that's a very interesting question. Did you have another thought? Well, yes, let me perhaps, yes. Okay, does it fit into any of this? Okay, let's put it down. What time do we have? I'll try to be a little briefer, please. Yes, please.
I wanted to ask about tunneling and the frustrated tunnel.
Oh, yeah, okay, tunnel.
And then also the P-N junction rectifiers and
Yeah, okay, and, oh yeah, those are PN, okay. And your thought was? Polarization of light? Oh, we had that on the exam already, right? And you're worried about it. Okay. Okay. Polarization in wires, yeah. Okay, let's try to... now, to answer this question, the Lyman-Balmer-Paschen thing is a takeoff from this. Namely, if you have your hydrogen atom, we're talking the Lyman... That's the spectrum coming out of hydrogen. So we have the hydrogen potential here, and we have the energy levels that result from quantizing something. We're trying to fit into this shape of potential. It's a closet. And we have a quantization condition that Bohr realized was that the angular momentum, n, has to be h bar. So he's forcing you to pick certain orbits. He says you can't pick any orbit you want. You must pick an orbit that has just a Planck length around it. And what comes out of that is these energy levels. Again, minus 13.6, minus 10.4, something like that. And then, because this is going as 1 over n squared, so this is 1 over 1 squared. This is going as 1 over 2 squared. This is going as 1 over 3 squared, so that's 9 into this, makes this like 9 into 12 makes 1.5, minus 1.5, and so on. Okay, well, this should be not quite enough. And then you have, that's 1 over 3 squared. You know what I'm doing. I'm dividing 13.6 by n squared. That's what these quantization conditions forced on me. 3 squared, the next one is 1 over 4 squared, 25, so it's 13 over 25 is roughly 0.5 electron volts. So again, it's a peculiar kind of spacing forced on us. There's a big jump here. This is, no, that's minus 3. Because I divide 4 into 13 is around 3. Right, 3.4. So the difference here is 10. That's what I meant. The difference is roughly 10 electron volts. The difference here is only about 1.5 electron volts. So you can see it's a peculiar kind of spacing. Forced on us again because of the shape of this closet, and we're allowed only those kinds of orbits. Okay, so the point is that in absorption, if you have a hydrogen atom, they're all in the ground state. That's the thing we pointed out maybe last time. They're all, because this is 10 electron volts, and the story we just told is that you have energy trying to shake them out of the ground state, but you need 10 electron volts, which represents 10 electron volts is maybe 50,000 Kelvin, and you have 300 at room temperature. So you're never going to get an electron up here. So if you shine light on hydrogen, it's going to absorb. It's going to absorb from here to here, and from here to here, and from here to here, for example. So you'll see this bunch of lines, and these are all in the ultraviolet. This is a very big, relatively big energy jump. So you're going to see an absorption spectrum in the ultraviolet of very high frequencies. You're going to see a whole bunch like this in the ultraviolet, and that's it. That's the whole absorption spectrum, because what you're doing is going from this state to that. On the other hand, what you did in the lab is you excited these hydrogen atoms such that, and here's your limit, such that you put electrons into these higher states by having a tube in which you passed electricity through. And that electricity was enough to send electrons into these higher states. Then you must have had more than, say, 15 volts here, so that it's big enough to take an electron 13 volts down and raising it up. And then the electrons start trying to go down in levels. So they cascade down. So you can get an electron up here, a free electron, it jumps into this level, and it emits light, or another atom. The difference is that these are all different atoms, because you have a whole tube full of gas. And the electrons, some of them fall right down to here. Some of them fall all the way down to here. And where they fall to, that really determines the major energy that they're going to see. So this one that's a relatively small energy compared to falling to here. So what you're going to get in emission, now you're doing emission because you excited the electrons, so they're emitting. You'll see those lines coming out, the high frequency lines, because those are the ones where the electrons, some have cascaded down to here, and then they'll jump to here. So out comes this line. Before it was absorbed, now it can be emitted. And you'll see this line, and you'll see this line, and this line. So you'll see this whole array of lines in the UV. And you'll also see, because some of the atoms, the electrons end up here and fall to here, you'll see this line, which wasn't present here. And so you're going to see a whole bunch of lines in here due to the fact that you ended up in level 2. The final state is 2. This is due to the electrons that end up in the final state 1. Does that make sense? That's what it is. And because of the big gaps here, this is only about 1 volt, This is 10. So this is way in the ultraviolet. This happens to be visible. So that's the ones people had seen, the ones ending up in this level, and that's the Balmer series. It's the series of lines corresponding to the final state. So you have the end final, the final state is 1 for the Lyman. For Balmer, the final state is 2. All the lines, and it's really dominated because of this irregular thing. The fact that they end up here really determines the range in which they come. And the ones that fall into this third state from higher states, all these higher states, they form, because this is the big deal, this is really that determines things, they fall into a whole different set, and those are the ones that end up in the final state 3. And these are also invisible because they're in the IR. This is the one that people knew about quite well because it's invisible, and this is in the ultraviolet. And so does that sort of answer your question? More or less, please. Now, I'll answer the question on pulses since I can. Yes?
So it depends on the final.
That's what determines the series, the final state, because that really tells the gross features. You see, look at the point here. Let's say you're in this state here. The biggest jump you could get is from 0 to minus 13. Okay, now, so that determines the whole story because the next higher level is 10 volts higher. So it's in a way different range. See, this whole set, the ones that end up here, are really determined by the fact they're ending up here. These are pretty much, because the difference between, look, this is 10 volts, so all of the rest of this is only 3. So you're going to get a spread from 10 to 3, but it's really determined, so you're going to get 10 volts down to, with a spread of about 3. Because all the rest of these only amount to 3. So you're really centered around 10. Well, yeah. And I think it's a very high value. Here, you basically, the most you can have is 3. The highest energy here is 3. So you're really in a different range. Here you're starting out with the range. Actually, the highest one is 13, I should say. Yeah. That's the biggest jump you could have. And it goes down from 13 to 10. In other words, the ones that end up here either started from here, or the maximum change is from here to here. And unfortunately, the diagram is very poor. It really should be. See, since this is 10, the whole rest is only 3. So it's about 1/3. So all you can do is go from here down to here, or from here down to here, and so the difference is between 10 and 13. So your whole batch is between 10 and 13. On the other hand, if you go from this level, you can go from 3 to, let's see, you can only go from here. Well, there's a whole bunch of lines starting at around 3. So it's just in a different frequency range. For this is the Balmer series. So as you say, it does depend on where you end up because that determines the major change. The thing on pulses is a very simple idea, namely that if you have a pulse of a certain width, if it's a finite length, that it cannot be a pure frequency, because a pure frequency would have that wavelength, that same wavelength, forever and ever. In order to create a pulse like this, you must mix various wavelengths together. One wavelength alone can't do it. So that gives you the idea that if you have a pulse that has a certain width, say in time, t in time, that delta f, delta t, is the order of 1. It turns out that you need a spread of frequencies. The shorter the pulse in time, the larger the spread of frequencies you need. Or in the case of, if we're talking about space, if I've localized a pulse in space, delta x, the spread of wavelengths I need, in other words, I have a certain wavelength in here, I can't localize a pulse in this space with just one wavelength. If it was just one wavelength, it would go on and on and on and on. So I need a spread of wavelengths. And so it turns out that you have a rule that looks like this. Again, delta x, delta lambda is the order of 1. And yeah, so from that, you can derive, let's see, delta x. If you use de Broglie's rule, well, it's a little bit tricky. De Broglie would say that P is equal to H over lambda, so you have dP. I'm going to get into a little bit of tricky business here, actually, doing it this way. But just let me say that the same argument that says that you need a spread of wavelengths will also say that you need a spread of because the momentum is proportional to the wavelength, as de Broglie says. If you localize a thing in a certain space, delta x, you will require a spread of wavelengths, which implies a spread in momenta, and the product of those two will be of the order of magnitude of the Planck's constant. Let's see. It's a little tricky to show this because, you see, delta. What I want here is h over lambda. The derivative of that is h 1 over lambda squared d lambda. So it gets a little bit tricky. But the point is that if you just, the physical feeling behind it is that you just need a spread of wavelengths to account for the localization of the pulse. Just that's good enough for you to know at this point. And the point is that I made a little deal about this is what goes on, why you need a large bandwidth. If you're trying to send a lot of information, very narrow pulses, you need many wavelengths in order to do that. That's good enough for this purpose, I think. Polarization, well, you know, that is actually on the in the answer sheet to the homework, or to the test, actually. The point is very straightforwardly, I thought, and that is if you have a wire, and you have an electric field with respect to that wire, an electric field along the wire pushes current up and down the wire. If the electric field were across the wire, the currents that it can draw are relatively small because the current can't go anywhere across the wire. So here you get no absorption, or let's say approximately no absorption of that electric field because it can't really make currents. It can't really get I squared R losses. Here, it can get currents running nice and freely up and down that wire. So here you will get absorption, so this wave will not pass. You get a yes absorption. You get absorption in this case, and so the wave does not pass. So here, if you want the wave to pass, you put the field perpendicular to the wires, and that field will pass, and so this becomes the polarization direction. It's a funny kind of concept. But that's the basic physics behind it. Try to think about, if you wanted to absorb, this will stop the wave. That will let the wave pass. If you want to absorb this, so this would be a good antenna, because you want to absorb the wave in an antenna, right? Because you want to receive it. Here, and in a polarizer, you want to let it pass. So that's the distinction. Yes, sir?
In this case, Professor, if you have a certain angle, then the intensity of it is cosine squared.
Right, the cosine squared. And the reason being that what you do is the electric field is the first stop that you do, and the amount that passes, you see, is the cosine of the angle. So the amount that passes is, I guess, the cosine of this angle. And so that would be the amount that passes. That's the field. But to get the energy, you square it. You always square to get the energy. So that's where you get E squared, or the intensity cosine squared theta, because the intensities are always square of the field. Hopefully that's enough. Please read the solution to the test, and you'll hopefully get the answer. Now, tunneling in FTIR is an interesting feature also. And that has to do, again, with the nature of waves, where they can proceed outside of where they should turn around. So we have two phenomena. One we did where we had an electromagnetic wave. This was actually a microwave. This is a demo we did, where we passed it through a block of paraffin at an angle such that it would be totally internally reflected. So we have total internal reflection, as it were, at this particular thing. And total internal reflection, you recall, is when the angle of refraction, theta refraction, is greater or equal to 90 degrees. In other words, the electromagnetic wave wants to turn away from the normal by at least 90 degrees, which means, or more, then it means it doesn't get out. And so that's your total internal reflection angle, or your critical angle, I guess they call it, critical, sometimes called. Okay. And that comes about when you use Snell's law. Sine theta incident N1 is N2 sine theta 2. And we're saying sine theta 2 is going to be 90 degrees, because now theta 2 is the angle in medium that you're going into, and this is theta 1. So in that, now N2 is 1, and sine theta 2 is 1 at 90 degrees, so that the condition is that sine theta of incidence is 1 over the index of refraction. I'll never get that N right. So that's the condition. This is the critical angle condition, where the refractive angle would be 90 degrees or more. Now that's the classical view, or the standard view. If you don't take into account the wave nature, if you do the wave nature, then the wave actually leaks out a little bit from this surface before it turns around. It leaks out a little bit, and the trick was we brought another surface close enough so that it actually could feel that little leakage, and we actually got the wave. If you bring it close enough, you can actually get it to feel that thing, and the wave will go right on through. So this is called the frustrated total internal reflection. And you can buy these, as I said, you can buy these instruments, FTIR instruments, where you can bring a surface close to this other surface and sort of detect what's in between. So what the physics that they're employing here is that the wave leaks out slightly. And if you get close enough, you can pick it up. It doesn't propagate very far into the medium, roughly about a wavelength. But if you get close enough, you can pick it up. So that is what it's called when you're dealing with light waves. When you're dealing with electron waves, we use the same phenomenon, namely, but what we convert it into is you have a metallic tip. These are supposed to be atoms of like some metal, and the electron's wave comes down to the tip, and it reflects back. Normally, the electrons don't jump out of the metal. So you have the electron comes down to the tip, and it's a particle, it's an electron, and it's a wave. So when it gets to the edge of the metal, it actually, like this frustrated tunneling, TIR, I'm getting mixed with TIR, it sounds like tunneling, but it's really total internal reflection. Instead of just turning around right at the last atom and going back, the wave function leaks out a little bit. It's wave-like nature. No, it doesn't wiggle. It just leaks out ever so slightly. So you're getting a little bit of leakage. Just as you get a little bit of leakage here, just a little bit outside the surface, such that if you bring another atomic surface here, the electron wave, once it reaches this surface, can propagate on as a wave. Just as when this one comes here, it leaks out a little bit. Most of it reflects off, but it leaks out a little bit. And if you bring this surface closer, you can get the wave to propagate through. Yes, sir. That was, you mean this one? Now, this one I actually didn't demonstrate in class. I meant to show you an animation of it where you could see a tip going over a surface and having an irregular surface like this. And if I brought the tip really close, the electrons would tunnel. We would call that tunneling. Where the wave function leaks out. And if you bring it close enough, you can actually get current to flow into this surface. I meant to show you that, but my animation didn't work. You can look it up, actually, under scanning tunneling microscope. Scan, tunnel. I guess they call it tunnel because they're thinking that this is an electron. And so